Okay, so good morning, everyone, or whatever your local time is. Just for anybody who's joined just at the end here, I'm putting a link to the repository page that you are viewing right now that I'm sharing the screen of. This is also linked to from the course website. And again, also for anybody who also just joined, I will put a link to the Etherpad, which is just a fancy name for a virtual whiteboard, which we can use during the day to store essentially information that is useful to refer back to, which maybe, if you put it in chat, it will just disappear. And if it's, it'll get split awkwardly over lines anyway, if you put it in the chat. Okay, so it's just over 1/2 past, so we'll get started with the course properly. As I said, the first session was just to help anybody who hadn't had a chance to log in yet, log into ARCHER2. So welcome everyone to Introduction to CP2K. This is run by ARCHER2 as part of one of our courses focusing on a particular package on ARCHER2, the National UK HPC service, and also in collaboration with colleagues of mine from the UKRI project, the ARCHER project on CP2K for machine learning and emerging architectures. And as well, we have an external friend of the family, say, from Kiel, University of Kiel, Anna Hain. So let me introduce the speakers today, the other speakers today properly. I haven't introduced myself, I should introduce myself. So I'm Arno, I'm based at EPCC, so we run ARCHER2, I'm part of the ARCHER2 CSE team. And with me earlier was my colleague Claire, who's involved in running and delivering a lot of the training with us. And also here is my colleague James Richings, also at EPCC, who will help support the first session with regards to any issues with job submissions and things like that. So thank you, James, as well. Then when it comes to the other speakers today, presenters, we have Professor Matt Watkins. So Matt is Professor of Chemical Physics at the University of Lincoln. And then we have later on Lele, who is a research fellow at the University of Nottingham in the group of Sanyan Ling. Sanyang will also be here at some point. I don't think he'll present directly. Lele has just joined the session. Perfect. Just as I was introducing you, Lele, thank you for joining. I will just add you to the...
Okay, hello, good morning, everyone. Yeah, Lele. Thanks, Arno.
Good morning. And as I already said, we have Anna Hain, who's Professor of Theoretical Chemistry at Kiel University, who will be giving a talk at the very end of today. But it's very nice to have all of you here. What we like to do with these courses is, before we get stuck into whether it's theory or practice or running stuff, presentations or running things on ARCHER2, it's always nice to just get a sense, especially with the online courses, when it's all like, well, this isn't Zoom or Teams, but Collaborate, whatever it is. It's just faceless names. But what's useful and nice as well is to know what people are interested in, why people are here, what you're trying to get out of the course. So let me just summarize first of all what we're trying to do with the course, and then we'll get around to doing a quick run around where we introduce ourselves and just very quickly state what your interest is in CP2K and why you're here, and that helps us who are presenting as well to get a sense of how best to provide what you're looking for. So the training materials here linked to are part of they're for the first session primarily, but they set out some of the goals of the course of all of today. So this is a starting point and the basis. So these materials, they're really, and the course as a whole today is really looking at giving you an introductory overview of some of the important features of CP2K. So CP2K is often referred to as a Swiss Army knife, I guess partly because it's most historically developed mainly in Switzerland, with contributions from elsewhere, of course, and because it can do so many different things. It's so flexible, such a useful tool. So with regards to the course today, we're trying to give you an overview sort of whirlwind overview of some of the important or useful things that CP2K can do. Will help you understand how to, or what's in a typical CP2K input file, how to prepare an input file, at least some of the things to get started with that. Looking at running CP2K in practice on an HPC machine like ARCHER2 in this case, understanding both the input and also the output, what CP2K produces. Then understanding what some of the key parameters are, and at least as a starting point, knowing the kinds of things you might want to look at and consider when it comes to parameterizing your problem. Some idea of getting good performance or getting good efficiency, and then really as a starting off point for you to be able to experiment with running your own simulations and how to take things further, where to find guidance. Now, in terms of the practicals in this in the course materials in this repository, there are a few different practicals. We will actually only look at two of them, namely energy force calculation, the first one, and then parallel performance, the last one. We will skip some of the other practicals relating to converging cutoffs, which is a useful step to be aware of when it comes to setting up your own calculations and parameterizing. We also won't do geometry optimization or in this session anyway, molecular dynamics, although there's AIMD, ab initio molecular dynamics later. Lele is giving that session. But these materials and practicals are here as well for you to look at. So, so as I said, the idea is to get familiar with CP2K, and this is the structure of the of this what's going to be the first session after our introduction. So with that, I'd like to go back to what I said we would do, which is to do a round robin sale. So we have the chat list, the list of participants in the chat is alphabetical. So what I suggest is that we take turns, and each of you just, if you can, unmute your mic and speak. If not, just type something in the chat, just to say, you know, what basically like what your research is and why you're interested in CP2K. So would and actually maybe what other packages you use, and maybe that's what other packages you use and where you know why you're interested in maybe CP2K. So with that, can I ask Anpan to start with introducing yourself?
Hello, can you hear me?
Yeah.
Yeah. Hello, my name is An Fang. I'm a lecturer at University of Surrey. So we just got a new project about the carbonation, cement carbonation. So I would like to learn how to use how to run ab initio MD with CP2K. So that's the reason I'm here today. Yeah, thank you.
Thank you. And Carlos, go ahead. And after Carlos finishes, the next speaker just go ahead.
Hi, well, I'm a postdoc in St. Andrews University, and some people in my group use CP2K, so I was like, I might as well learn a bit. I usually do just, you know, DFT, like more molecular DFT rather than solid state or like periodic DFT. So yeah, I'm just interested in learning a bit about that. And I use typically things like Gaussian, ORCA, Psi4. I've used a bit of MOLCAS as well. Anyway.
Hi, my name's Chris. I'm a first year DPhil, and our group has a lot of knowledge on VASP. We model batteries, and we're looking at getting a little bit more knowledge on CP2K, especially for solid structures with void spaces and that sort of thing.
Hi, I'm Daniel. I'm also doing a PhD at St. Andrews. I'm going to computational stuff. So just been using Gaussian and CP2K for that for the last few months. I thought I'd come here to learn a bit more about how to use this software.
Yeah, Dimitris, if you can unmute, please feel free. If not, you can put something in the chat. Okay, go ahead. I can't remember your name, Federico or something from the registrations.
Yeah. Hi, my name is Fred. I'm a postdoc at the University of Leeds. I'm running more classical MED, but the next step of my project will include some QMMM and ab initio MED, and I plan to do this with CP2K. Thank you.
Dimitris, do you want to try again?
Hello, everyone. Can you hear me?
Yes.
Hello.
Go ahead.
Oh, great. So my name is Guozhen, and I'm very glad to participate in this virtual workshop. I'm from China, and I'm a researcher in University of Science and Technology of China. I'm particularly interested in the new features of CP2K, like the excited states calculation. And I have just read some paper published in JAX, I think a couple of weeks ago, and I'm interested in how to do that in CP2K. And meanwhile, I'm also looking into the ab initio molecular dynamics with the enhanced sampling that implemented in CP2K. And
Thanks. I'll just interrupt. And yeah, I guess people can see Dimitris. Thank you for adding in the chat. As a mystic MD on RNA protein systems and interested to try GROMAX with CP2K for QMM calculations. Well, it's good you mentioned that. So that sounds very familiar to me because I was involved in a project that helped to develop that that interface between GROMAX and CP2K. So there's a link in the end of the course materials of this repository that links to some of that, so you might find that useful afterwards. Okay, thank you. Jay?
Hi, can you hear me?
Yeah.
So I'm a PhD student down in Southampton University, and we use CP2K as part of our workflow. So I really just wanted to get a better idea of how to use it myself and change the parameters. Because currently I'm using it, I guess, a more black box way, which is always not really ideal.
Right, so I'm Joan, I'm an RSC at the University of Lincoln, and I'm developing a tool to automate workflows to train ML force fields and run MD simulations with them. So the ab initio engine that I'm using at the moment is CP2K to generate ab initio data to train these workflows. So yeah, just thought I would learn to use it.
Hiya, hope you can hear me. So I'm a first year PhD student at the University of York, and I'm originally a synthetic chemist, and no one in my group does or uses CP2K. They tend to use Gaussian, so I'm trying to understand CP2K to model metal organic frameworks and get their density of states and other information for battery applications as well.
Hello, my name is Mateusz. I'm a PhD student at the University of Birmingham. My research is in modeling mechanochemical transformations. We mostly use CASTEP for this and starting to use Quantum Espresso. And I thought I would also learn CP2K to see kind of what's available in software. So that's why I'm here.
Can you hear me? Yeah. So hi, I'm Maxime. I'm a postdoc in Leuven University in Belgium. So I'm quite used to study excited state properties in molecular systems in molecules, but here I am starting a project on excited state properties of periodic systems, and for that I intend to use CP2K for its versatility. But so yeah, that's why I'm here.
Thank you. And then, do you want to try using your mic? or put something in the chat otherwise. In that, it seems not to be working. In that case, Natalia, do you want to go next?
Hello, I'm Natalia. I'm an academic at the University of Sheffield. I study materials such as photocatalysts, and I already use CP2K, and I would like to learn more about excited state calculations.
Hello everyone. Hello. I'm Nitin. I am a PhD candidate at the Institute of Technology, Gandhinagar, and I am looking forward to use CPK for QMM calculations on proteins.
I can see you've unmuted yourself, Rocco, but we cannot hear you. So maybe you can put something in the chat and we can come back to you possibly. Shivam, do you want to try?
Hello everyone, I am assistant professor in IIT Kanpur and I mostly worked on metals during my PhD and postdocs. I used VASP quantum espresso. So now I have a project where I will want to work on composites of polymers and ceramics. So I want to get started with CP2K and get the feel of it about and use it in my current project. Thank you.
Hi, so I'm Tom. I'm a PhD student at the University of Oxford, and I have experience using VASP and CASTEP for the development of machine learning potentials for materials, but future collaborators and sort of the next project I'll be working on prefer to use CP2K, and so I wanted to get a feeling for how these things transfer and how to use it in a similar kind of way.
Hello? Hello, can you hear me? Okay. Hello, I'm Yingguo, and I work on the initio thermodynamics in the domain of earth sciences. I work in the University of Science and Technology of China and UCL. So I have been using VASP and quantum espresso a lot in the past. In this course, I want to learn the features of CP2K and also the practical things. Thank you.
Okay, nice. Rocco, do you want to try again?
Yeah, can you hear me?
Yes. Mm-hmm.
Oh, nice. Okay, finally. Hello, everyone. So my name is Rocco, and I'm a research software engineer at CSCS, which is the equivalent of EPCC for Switzerland. And I've been working on integrating some linear algebra library in CP2K, but I never used CP2K myself. So I thought this was a very nice occasion to actually learn a bit more about the software itself.
Okay, great. Thank you. Oh, you've yeah.
Okay, my name is Marcin Maździerz. I'm from Poland, from Polish Academy of Science. I'm after PhD, and I deal with nanomechanics and condensed matter physics, and mainly I'm interested in mechanical properties of crystals, 2D and 3D, and quite intensively use ABinit. But because this classical plane wave code, I'm looking for codes with different approaches to calculate bigger systems. And CP2K is one of the choice.
Okay, great. Thank you very much. That's really nice. I think it's really nice just to get a sense of what what people are doing and also why you're interested in CP2K, and perhaps it's also interesting for you as participants to just see what other people are doing and why, what other packages people are using and why in some cases. So unfortunately we don't have, obviously with these virtual courses, the opportunity where over coffee or tea or lunch you can have a chat about what you're doing and whether or not what package you're using, which is a shame. But well, of course, if you want to do use a chat during the breaks or during lunch, and encourage you to try that. Okay, so in the schedule, we have the next session starting. Well, I can just have a quick look, show you the schedules, just to remind you what the plan is in principle for the day. So we've done setup and login. So we've just here in the introduction. So in principle, 10 o'clock we would start with the first practical. And I think I will just start now, and then we can take a break, or at least we can let you get on with something yourself for a bit, and then jump in and out again. And we'll basically do that and look and go in between. We'll sort of alternate between you trying things on ARCHER2, and then sort of maybe discussing it a bit between now and at 11 o'clock UK time. Okay, so with that, having said that, the first step, if you haven't done so already, is to log onto ARCHER2 and to clone this repository with the command as I put in the Etherpad link. So color is a bit weird, but here anyway, that's the command for cloning the repository locally. So if you go to, we'll start with contents. So there, so let's get stuck in. So as you maybe already know, so CP2K can do a lot of different things. We've said that. There are various sort of terms that might come in and just useful to be aware of. So when it comes to lots of DFT calculations, solutions of the Kohn-Sham equations in CP2K, that falls under what historically was the quick step or QS module. So whenever you see a reference in documentation, manual, keywords to QS, that refers to quick step, which uses this combination of Gaussian and Plane-Waves method in the augmented version to solve solve the wave functions of the electron density. We won't go into details really about the algorithms, but this is just a brief touching on a couple of terms that are relevant that you will see appearing in the input files and in the output, and that in some cases speakers like Matt, Lele, and Anna will touch on and mention in a bit more detail later on. So the orbital transformation, or OT method, is this minimization scheme that gives you this wave function optimization. Yeah, it has some advantages in CP2K compared to other methods and other packages, which there's a lot of literature that you can read up on with regards to also the different scaling properties. In this case, the orbital transformation scales cubically with system size. There's also linear scaling routines, but that's different issue. So then there's the question of what functionals to use. As always with DFT calculations, the question about what is included in the in your DFT approximation in your functionals. That will be the topic of so Matt will talk about the standard sort of quote unquote standard DFT, hybrid DFT, and that we'll talk about more later. So some of these details, if you're not familiar with, they won't mean that much. These terms like local density approximation, the gradient approximation, and won't mean so much right now. But again, this is basically a question of how accurate do you need. What you need, because there's a big increase in computational cost that comes with using, in principle, higher accuracy methods, more realistic methods. So HFX is something that you'll see popping up again and again. That refers to Hartree-Fock exchange for use in hybrid methods, so with hybrid functionals, which Matt will talk about later. So optimization, CP2K can do geometry optimization and cell optimization. It can do ab initio molecular dynamics for AIMD, a variety of approaches. QMMM, as some people have already mentioned, both internally using purely CP2K itself for both the QM and the MM, but also, as Dimitris mentioned, he was interested in using an interface to GROMACS, where GROMACS handles the MM and basically just calls out to CP2K to compute the QM energies and forces for the QM region of interest. CP2K can also do classical MD. and it can do sort of transition state finding with methods like nudge elastic band or NAB. Energy pathways, a variety of things. Metadynamics, there's some built-in stuff, and also the package that's used by a lot of different packages like Romex, etc. can plug into lots of different packages. Plumed. A couple of points about the code base, which may not be relevant unless you actually care about developing or building or anything like that. So it's written in Fortran, and we'll talk about parallelism in a bit more detail later. So it supports parallelism in multiple ways. It's got quite a few internal libraries or libraries that were historically developed to do linear algebra for the kinds of matrices that CP2K generates, that the problems in CP2K generates, which were then in some cases spawned off as separate libraries and then or incorporated. So an example is a DBCSR library, and that Rocco mentioned he's working on something integrating a linear algebra library. So this is constantly being developed by the developers as well. With regards to parallelism, you may or may not be familiar with MPI, which is a type of parallelism, message passing. It's a way of making use of many processor cores, splitting up a problem. And in this case, the parallelism, a lot of the MPI parallelism that allows CP2K to scale to large core counts has to do with parallelizing over the real space grid. So there are real space grid projections projections of the operators. So there's various coarse and fine-grained grid resolutions, and these are kind of managed and parallelized over in a way that's allows CP2K to scale quite well. There's OpenMP threading. So OpenMP is another way of getting parallelism. So the M in MPI stands for message passing. So the idea there is that processes basically send messages. The problem gets decomposed somehow, and different cores run different parts of the problem, and these cores send messages to each other. Threading is just another kind of parallelism, and that's used for in a number of different subroutines. So OpenMP threading is kind of spread throughout CP2K in various places. CP2K does support offloading to GPU, and there's been a lot of active development over the last few years. On ARCHER2, there's no GPUs. There's a very, very small GPU testbed with AMD GPUs, but unlike many of the large European or US or other systems, ARCHER2 doesn't have GPUs, so it's not relevant really for the discussion today. And as I said, there's a number of libraries that CP2K depends on. Some of these are internal to CP2K. There's a lot of external libraries, way more actually than just these three, which have historically been important ones. But yeah, that's you won't really, as a user, if you're starting to use CP2K for the first time, you don't really have to worry about this either. Either the installation that you're using on an HPC machine has or doesn't have these libraries built, which may mean that you either don't get some of the functionality you want. If you don't get it, you say, well, I want this functionality, and then you can request maybe that it's rebuilt. In other cases, it may be that it's possible to get better performance. So it's useful to if you're starting to use CP2K more for production usage to look into the performance and to sort of look at whether all the libraries that could give more performance have been built, and that CP2K is using those libraries. But that's details that are not relevant for preliminary introduction. What's also relevant really right now is how to build CP2K, because we're just going to use an ARCHER2 version that's installed, which is typically what you'll come across on HPC machines. I know CP2K has started to become available through package managers in some Linux distributions, so that you can just do apt install CP2K. It's also available now increasingly as a containerized piece of software. But on many of the large machines, HPC machines that you're using CP2K on, typically you'd expect to either for the sort of service support to maybe install that, or for you to go through the process of installing it. Okay, so if you've not already logged on to ARCHER2, then this is a good time to do so. It mentions here that you can use the -XY option to visualize anything. I don't think it's relevant really for the two exercises that we're doing, so you don't need to use this visual option, so you can just use SSH as is. So yeah, as I said, you can clone this. So just to clarify for any of you, so I know some of you are already existing ARCHER2 users, some about I think half of you or something are not. So just to make you aware, ARCHER2 has two file systems. There's a file system which is mounted starting with /work, and the other one is /home. So when you log onto ARCHER2, you automatically get put into your home space on /home. So when you log onto ARCHER2 and you type pwd to get your working directory, you will be on /home/ in this case TA145, which is the project code associated with today's course, /TA1454 / your username. But what I suggest you do is that, as it says here, you navigate to your directory on /work and clone the repository there. Why? It's because this repository includes the input files and the job scripts that you're going to submit to run things, and the home file system is not accessible from the compute nodes. And the work file system is specifically meant for high performance input-output. It's a parallel file system, so that's what is visible from compute nodes. So that's what you should be using. So if you navigate to the directory CP2K practical files, which is just part of this repository, if we go one level back up to the base directory, you can see the directory CP2K practical files. If you go there and to exercise 1, and have a look at these two files there. There's the CP2K input file, input_h2o.imp, and this job submission script. So let's have a look at, so the CP2K input file format is as follows. So it contains information about your system, your parameterization, and the kind of calculation you're asking CP2K to do. So the general format, it's kind of old school. It's kind of, there's indentation, which is optional, but it's very helpful in terms of keeping clear to a human what each section is doing. So you have different sections with different keywords and different parameters for each section, specifying options for that section. And comments can be made with a hash. So to be a bit more concrete, CP2K input files, they typically require 3 main sections: the global section, the force eval section, and the motion section, if relevant. In the global section, there's global settings like the kind of the name for your project, the name for your run, the run type, which is the main thing, telling CP2K what type of calculation this is. Is this a MD calculation? Is this a geometry optimization? Is this an energy force calculation? A global print level, which we'll get to. Then in the force evaluation section, you set up options like DFT options, force field settings in the case of MD. So in that section, you choose a method to compute the forces, for example, quickstep for DFT, or QMM for the QMM, FIST for classical force field calculations. Then for the density functional section, you will choose your basis set, potential, file name, so where to get these inputs from. Then the algorithm for solving the Kohn-Sham equations and producing a wave function is the so-called SCF, self-consistent field calculation. So you'll see this a lot in the output of CP2K runs. So you'll see that it's going through an iterative process of SCF iterations, and there are 2 levels of this. There's an outer SCF iteration and an inner SCF iteration. And then you can specify various things like tolerances and how many steps you're willing to allow the algorithm to proceed to try and get the wave function solution to within the requested tolerance. The orbital transformation section also has similar settings. Then there's a section on the grid. So on your multi-grid. So multi-grid refers to this grid of different coarsenesses or different fineness levels. There's parameters like the cutoff, two different kinds of cutoffs at least, which are there's an exercise in practical which we won't do today about how to choose those parameters. Then there's overall quick step parameters, your choice of correlation exchange, functional. Then finally, in the subsets section, there's information about your cell, your coordinates, and then the kinds of atoms that are in your simulation, and you would have to describe each what basis set and potential to use, elements to use for each kind of atom, which will then be fetched from, will be attempted to be fetched from the basis set file name, basis set file, and the potential file that you've named higher above. So I would suggest you have a look now. You just spend a minute having a look at the H2O input file, and I'll just take a quick pause. Yeah, in fact, why don't you have a look at the input file? There's a link here to the CP2K manual, which in principle can be used to look at what the options are and what the defaults are, and then we'll continue with this. So I'll just take a quick break for 1 minute to give you a chance to look at the input file that's mentioned. Oh yes, Maddie, you can just use whatever you like to look at the input file. If Vim works for you, use Vim. Cat just concatenates, prints out the output of the file to screen. So that's just the difference between the output and actually editing. And Joan, yes, advantages of doing QMM with GROMACS or CP2K versus using only CP2K. Well, some of the advantages are that GROMACS supports, I think, a wider variety of classical force fields. I think it's so the MM functionality in CP2K isn't really used that much, from what I understand, and really, I mean, part of the reason why when the interface was created to GROMACS is to allow people who are interested in new biomolecular simulation to use GROMACS to actually essentially steer CP2K, so that the question of how to parameterize and use CP2K is kind of filtered out, and you can use your existing way of pre-processing, preparing input files for GROMACS, which will be very familiar to users who are doing biomolecular simulation, of course, especially using GROMACS to do. So it's a combination of basically meaning that GROMACS is a core MD code, so it's got lots of stuff that's useful for that, and is a useful way, is kind of maybe easier to use or broader functionality or more up to date in some cases with regards to force field support than CP2K. Okay, that was more than a minute, but there's some questions that came up, which of course are useful to address. So yeah, the parallelism will come later. There's an exercise 5 we'll talk about. Yeah, we'll talk about parallelism exactly like Rocco was saying. Yeah, so that will become clear in a bit. Okay, so hopefully you've had a look at the input file for exercise 1 and sort of recognized some of the sections and had a look. Okay. So yeah, so some of the parameters. Obviously, there are a lot of parameters that you don't specify, and any parameters that you don't specify in your input file, they will still take some default values. So it is useful to be aware of what those default values are, and one of those values is the cutoff, for example, if you don't specify it. So there's exercise that you can do in your own time. Maybe that is a second exercise that talks about how to choose that. Now, to get insight into what some of those other default values are, one way to do that is to change the verbosity of the output file. So there's a variable called print level, or keyword called print level, which can appear in a global section or within individual sections, subsections, to control the verbosity of output. So if you put print level, I think in the example is in exercise 1 is low, but you can change it to medium. It suggests below that you do that and try that. So that will give you more information, and in particular, it will make it very explicit what all the values are for parameters that you've not set. So, okay, just a note on units. It's useful, you need to be aware of what units are being used, obviously. So check the manual for that. There's some additional syntax you can use to declare variables within your input file. And finally, as I already said, you can use you can have comments with a hash. You can include other files with the syntax as well. I mentioned that there are you have to specify the basis set and the potential for each kind. For example, as follows here. For hydrogen, that you're saying this basis set and this potential choice, which will be fetched from these files respectively. Now, you might say, where are those files? They are part of the CP2K distribution. And typically when you're using CP2K on a machine like ARCHER2, then CP2K will automatically find those files because they're part of the distribution, and because an environment variable called CP2K_data has been set typically by an environment module that's loaded. So when you start to run here on ARCHER2, the first step is to load a module to make CP2K available. And that immediately sets the CP2K data directory, which makes those files available. So you can look, for example, if you're interested, you can look to see how this how hydrogen, for example, appears within that basis mollopt basis set by running this grep command. Okay, so as I said, if you're going to run CP2K, you on ARCHER2 you load this module. There are various versions of CP2K installed. This is the latest one, the most recent one, and the current default. So I suggest you use this one for today. There are, and here we come to what Rocco was saying. So there are actually a number of different CP2K executables. There are potentially more now for running in parallel, but there's one called CP2K dot with the extension .popt, and the extension is just there as a convention to denote the historically the pure MPI, which is no OpenMP threading, but now since I think since CP2K 7.1, that no longer exists really as pure MPI. It actually is a link to another CP2K executable, CP2K.psmp, which is typically the one you almost always use, especially on HPC machines. And the CP2K.psmp executable is parallel using both MPI and OpenMP. And if you want to run pure MPI, you just you run with one OpenMP thread, which in fact I think is that's the default for the job script submission in the first exercise. So next step is for you to actually, in exercise 1, to actually run CP2K, and I'll let you get to that in a minute. But I want to explain to you the following job script, which is the same job script that you'll find in the exercise 1. So if I explain it now, then you know what means what and why it's the way it is on ARCHER2, which will be relevant for the rest of today. And by the way, if you are part of this course, then the accounts you have under this project TA154 will remain active for up to 1 month following the end of the course. So up until May 8th, up to including May 8th, and there should be some budget left probably after the course to be able to allow you to experiment with running things. So this will be useful to know about. If you're already an ARCHER2 user, some of this may already be familiar, but useful to review. So as typical with job scripts, you have one section of the job script that specifies your resource request to the scheduler to allow it to schedule your job and eventually execute it using whatever resources you have requested. Then the rest of the job script is just what you're trying to actually do in your job. So let's focus on the resource request. We've given our job a name here. We've said we want one node, and on ARCHER2 nodes are so-called exclusive usage, meaning that you can never use only part of a node. So you request resources in units of nodes, essentially, meaning that even if you're not going to use all the cores that are on a node, you will still be paying for at least one node for the duration of your job. Then we are two options which you specify here to the scheduler. One is tasks per node, and the other is CPUs per task. So this maps directly onto the number of MPI ranks that we want to run CP2K with, and the number of OpenMP threads per MPI rank that we want to run CP2K with. Now, to clarify now, why are we using these numbers? Well, first of all, we're saying that we're going to run 128 ranks, so 128 instances, say, of CP2K being launched in parallel on each node. In this case, there's only one node, and we're going to only use one thread, essentially, in effectively, really what this means is reserve one core per task. Why 128? Because ARCHER2 compute nodes are fitted with two AMD EPYC processors, each of which has 64 cores. So you have 128 cores available on each ARCHER2 compute node. So that's why we use 128 tasks, i.e. 128 MPI ranks. Question from Gaussian. If the Slurm system does not have SRUN but only MPI run and MPI exec, how to modify the line? Yes, so in that case, so just to clarify the question, it's that you basically have the scheduler that schedules your resources, which could be Slurm, could be another scheduler, and then you have the srun command, which will run the MPI parallel, which will launch your program in parallel using MPI, which is actually associated with the MPI library that you're using. So in principle, the scheduler and the MPI library are kind of distinct. But srun on ARCHER2 by default will use the Cray and Pitch MPI library. So to adapt this script to another system, like you're asking, you almost certainly want to get rid of the hint equals no multi-thread and distribution equals block, or at least there's no reason to suspect that they need to be specified explicitly for your system, that you might need to find additional guidance for your system. I wasn't planning to really go into detail about why those particular mappings are chosen for ARCHER2. The srun command you will simply have to replace with MPI exec, and depending on the setup of Slurm on the system that you're running on, the options of how many tasks to run for, namely how many parallel instances of CP2K the parallel application launcher MPI run or MPI exec should be launching, will either need to be specified explicitly with a -n or -np option to be equal in this case to 128, or if the scheduler on your system is set up in the same way as an ARCHER2, the -n or -np will automatically be picked up by srun or MPI run or MPI exec from your resource specification in the scheduler. So it really depends on your system and how it's been set up, how the scheduler has been set up, and how srun is being configured. As you see here, when we launch the executable here on ARCHER2, we are not specifying any options to srun saying how many parallel instances of CP2K, how many ranks, how many MPI ranks. Yeah, so I suppose there that goes in. Yeah, your capital N is probably the number of nodes, and then lowercase n is probably the number of MPI ranks or parallel instances, assuming that you have, presumably on those nodes that you're running on, you probably have 32 cores per node, I suspect. So on ARCHER2, as I said, we don't explicitly specify that, but we do have this additional thing here, which I was going to come to later, but I'll mention now, which is an important thing to be aware of on ARCHER2 specifically. It is in the example. It's all mentioned in the example. So if you're a regular ARCHER2 user, you'll be familiar with the ARCHER2 documentation. And there, under research software, if you look at CP2K, you will see some guidance, including standard job script. And this job script has a similar expression here. So what this does is, it setting the srun CPUs per task, makes sure that srun makes the correct allocation of OpenMP threads to reserved cores as reserved by your resource request, as specified in your resource request here. So basically, I said srun on ARCHER2 automatically picks up the tasks per node specification for the number of parallel instances of CP2K. However, it does not automatically pick up number of CPUs per task, and that needs to be specified explicitly by setting this environment variable. Or alternatively, you can specify an srun option, but this is the way it's conventionally done. Okay, there is another option here called OMP places. This on ARCHER2 is recommended to set the affinity, which means to affinity meaning where each thread, where each OpenMP thread runs, that it's sticks to a particular core. This can have an impact on performance in ARCHER2 in some cases. So a final note about when you run this, where the output goes. So by default, the output will go to standard out. And in other words, when you run on ARCHER2, it will go to a file, an output file that appears after your job has started, called slurm-a-number.out. If you want to, which can be very convenient, have this into a file that is easier to remember what it was referring to, for example, using particular parameters that were in your run, then you can either pipe it into a file that you name, or use the -o CP2K option to name an output file. And you can name it whatever you like. Okay, I'll stop talking and give you a chance to actually do exercise 1, run CP2K. So we have a reservation we have 15 compute nodes available to us to use, where unless they're all taken, your job should start running straight away. So when you submit your compute job, you should use the sbatch command to submit, and you should include these 2 options. And what I have yet to give you is this reservation ID. So there's a different reservation ID for now until 12 o'clock, and one for the afternoon as well. So I will just give you the reservation ID. I will put it in the chat and also in the Etherpad. Okay, so the reservation ID in bold is the one you want. Okay, so I suggest you go ahead, run that. You can also, you could also use a short queue, but we have this reserved. So unless you're having issues with throughput, then just use a reservation. Good question, Maxime. No. So the reservation ID, you only put in here where it says reservation ID, where it says reservation, you just use the word reservation literal. So I perhaps should have put like something around this reservation ID to make it clear that this should be substituted, but the QoS that you submit to is simply called reservation literally. So I suggest that you run the simulation, have a look at the output, whether it's Slurm or whether you've called it something else, and have a look to see how many steps it takes to converge the SCF run. And once you find that, how many steps it takes to converge the SCF run, you can put it in the chat. Let's see. Also, if you find the total runtime, have a look and put it in the chat just to know how people are getting on. Okay, so hopefully people can see both my terminal window and also the screen, also the exercise. So have a quick look at the output file. So there's a lot of information at the top talking about global terms, number of lots of information that you specified, including the total number of message passing processes, number of OpenMP threads, information about the memory. Then you can see it starts the quick step module. It talks about the different SCF criteria, and then so what you see ultimately is that it says SCF run converged in 6 steps, but actually there were already a set of 15 steps before this. So this goes back to the SCF algorithm having 2 levels, level 1 and level 2. I'm not the right person to tell you about the exact difference between what happens in level 1 and level 2, but there's an outer loop and inner loop, in other words, and the outer loop has an SCF max SCF setting of 15, and the inner loop has a max SCF not set, I think. Oh no, set to 1. Sorry. Is that right? Oh, it's the other way around. So so here it is performing one iteration of the outer loop, in which it performs 15 iterations of the inner SCF loop, at which point SCF has not yet converged. Then it will continue with the next iteration of the outer loop to do another set of, in principle, 15 iterations maximum of the inner loop. But after 6 iterations of the inner loop, it actually has converged. So in fact, it's converged after 15 plus 6 iterations, you could argue. So undoubtedly something happens between the first and the second iteration of the outer loop. But yeah, so that's a summary of that. And the max runtime. So if we keep on scrolling, there's a lot of information here about the run. And then once you get to the bottom of the output file, it talks about floating point operations to do with different matrix sizes, linear algebra. It gives you a warning, which is interesting, about the number of ranks. And at the very end, after listing the publications, there is a timing section, which is useful because there's a lot of detailed information about which subroutines are taking the time. But at the very top level, if you look at the top line here, CP2K itself, the average, the time, and this is average, either average or total maximum across all the ranks. So at most, it will take 5.3454 seconds. So I think that's what people are finding. If you've managed this, then go ahead and change the print level and experiment with that. And if you've managed that, then have a look at restarting the wave function. I will just answer some of the questions that have come up that I can see. Yes, Matt, thank you. That is the right suggestion. So you probably, Mateusz, you probably haven't added the -- QoS equals the word reservation. And a question about CP2K version 2024.1. Yes, good question. This is not currently installed in ARCHER2. I think we're just testing and install with the regression tests, making sure that it's all correct before making this available. It's a long story, but we're experimenting with moving to the toolchain build, which is the automated build that the developers have put a lot of effort in over the past few years. So historically, we've been building some of the libraries separately and linking to them explicitly. It's not so much problems with compilations. I mean, it works, but we're just checking. Don't want to make a we're just going to check before we make that available. Make sure it's all right. But yeah, we plan to make 2024 available soon. So yeah, so I suggest people, if you haven't already tried changing the print level, and what you should see is essentially, you know, very usefully, not giving you all the information, including speed of light and Planck's constant and a whole lot of other stuff, but obviously also slightly less generic information that is the values of keywords that you've not specified in the input file. So there's simply a lot of more information there. So that should be useful for debugging and understanding what CP2K is assuming when you're starting out and are not yet familiar with that. If you check and try using the restart wave function, so CP2K outputs a restart wave function, which you can use if you have partially completed a calculation and want to continue SAF convergence from a wave function that's already partly converged. For example, because your job got cut off or something like this, or you just want to for whatever reason. So to do that, you edit the input file and you actually specify this keyword wave function restart file name as being equal to the restart function that was saved automatically by CP2K when you ran it the first time. And also you change its keyword SCF guess from being atomic to restart, and that means it should use. So does anybody, if you've tried running, can you see how many steps it takes to converge and the total runtime, what that is now? Oh yeah, Rocco. Okay, yeah. So the tool, I am referring to the CP2K toolchain. That's right. So okay, so it'll take it's good that it'll take a long time, because by the time it's switched to SPAC, then maybe Archer or ARCHER2 will have switched to SPAC possibly, or we simply go back to building things, libraries independently. It can potentially save a lot of time, as you know, I guess, because it just means that all the exact configurations options are all there, and it should be downloading the exact right compatible versions of all the libraries without you having to work it out. So if anybody has an answer for how many steps it takes to converge now and what the total runtime is now, please feel free to put it in the chat. One step and 1 second. Yeah, that sounds about right. Well, 1 second is actually quicker than I found, but indeed it's only one step. Why? Because what you were reusing was the converged wave function from the last simulation, from the last calculation run, which was already converged. So with all the settings that you asked for. So obviously you were feeding it as an initialization, restarting on the already converged wave function. So it just does one step. It doesn't do 0 steps. It does one step and says, all right, we're converged. So that's not unexpected. So yeah, and therefore it takes much less time. Good. Okay, we have about 20 minutes left in this session. So then, as I said, needs at least 2 steps to make sure the convergence. Well, it depends on what your starting point is. Maybe others like Matt can comment, but exercises 2, 3, and 4 in these materials are bonus. You can refer back to them later, do them in your own time. What I wanted to skip ahead to now in the remaining 20 minutes was exercise 5, talking about parallelism and giving you some practice with that. Maxime, so this is sort of where my knowledge isn't broad or deep enough with regard to knowing how generally you can use the restart file. So maybe the real experts can comment. Thanks, Matt. Okay, so exercise 5 in the time we have remaining, which you can also, if you want, to look at it in the break as well. But So basically, we're going to have a look at seeing when you have a size of calculation, how the compute time and how this compute time to complete your calculation scales with different numbers of cores that you use, how that differs for all else being equal, simply having a larger system. So there are 3 CP2K input files in the directory for exercise 5. Exercise 5 has a part 1 and a part 2 is a part 1. So there's 3 input files. In the interest of time, you could focus on just the largest one and the smallest one. This is for 32 water molecules and 256 water molecules, or atoms making water molecules, actually, probably. And so if you run both of those, and now in this case, the default job script, I think, still has the specification of 1 node, but you can try running on 2 nodes and on 4 nodes as well, say both for the smallest system and for the largest system. And what you should have a look at then is record the time. So this top line in the profile that I pointed out, where it says CP2K and then the file, you can easily get that out without opening the file by simply doing a grep for CP2K followed by at least 2 spaces, then the name of the output file. Then you get the output with a time like 5 seconds in the last case. Now, ideally, we would love it if for any given system or for any given simulation that we're trying to run, if we use twice as many cores, we should get a result twice as quickly. If we use 4 times as many cores, we should get a result 4 times as quickly. So in other words, we want the speed up to be however many more cores we use as originally. So if we take the speed up in this case as being the time to run on 1 node, which is the minimum you can pay for on ARCHER2, divided by the time on however many nodes you're running on, compute that and look at also what the parallel efficiency is. In other words, what the speed up is compared to how many more cores you're running on. And if it was 100% parallel efficiency, that would mean if you use 4 nodes, it would be 4 times as fast on 1 node. So next step is to try this and see what results you get. So like just give people 5 minutes to play around with this for 32 H2O32 and H2O256. If you're finding that your job is queued, is just staying queued, that could mean that the nodes in the reservation are all being used currently. And you could, at the beginning, it mentions here when you submit with sbatch, where we said that the reservation ID, I also said alternatively, when a reservation is not active or actually at any point, you could actually submit your job script, including for part 5, exercise 5, with the following command. Instead of specifying the reservation, you could do --QoS equals short, and as long as your job is less than 20 minutes, which it is, then that will run in the short queue. Yeah, if the reservation is busy right now, that might be quicker, but it's not guaranteed. So I'll just give people 5 minutes to play around with this. Yes, that's actually a very good question, Maddie. Once you've submitted the job, can you edit the job script or input file, or would this mess up the submitted calculation if not running already? It's a very good question, and this can catch you out if you don't think about that. So it's good that you're thinking about it. So you can change the job script, and that will, in principle, not alter the job you have submitted, because at the point in time when you run the sbatch command, that is literally you handing over your job script to the scheduler, which then takes it and then uses the initial part of it, the sbatch stuff that starts with #sbatch to schedule the resources, and then keeps that job script ready to run. So you could in principle change the job script after you've submitted, and it won't change the job you've already submitted. However, the input file is another matter, because your job, you don't know when your job's going to start running. When it eventually runs, if at that point the input file is in a different state than it was when you submitted the job, it will read whatever it is at the time it starts running. So that's why it's useful to have different input files names and specify those explicitly for different jobs. So that's how it could potentially mess up something you've submitted if you start editing the input file. Yeah. So does anybody have any conclusions, any times for maybe even speed ups, maybe even parallel efficiency for some of the runs with either 256 or 332? It's weird. Okay, weird. Weird how. The more nodes you put, the longer it takes. Well, that can happen if you're doing it with a small, for example, with a small system. So yeah. So basically, if you have so little work to do calculationally that you're trying to split it up over many cores, then essentially the overheads are larger than the benefit you're getting. There's not enough work to do. So that's why a larger system like the 256 is more likely to scale better. So yeah, that's the basic idea. So it's useful to check this. So don't just arbitrarily run your system with more cores. So basically, this is a very simple exercise. That's just, yeah. Thanks, Maxime, and Carlos, and Gaussian, and Chris. This is simply a simple exercise for making you realize that what you want to do is to check what. I mean, in a way, compare what is the smallest scale you can run on, and on ARCHER2, even if you could run your problem on one core, you're still paying for one node. So you might as well compare your parallel scaling in terms of getting bang for buck, money worth, to how long it takes on more than one node, sort of in multiples of nodes. So how much faster on 2 nodes, or how much faster on 4 nodes. So in interest of time, I think I will summarize that and check to see whether you get this. I'll put it in the Etherpad. Thanks. Somebody's put their timings in. Okay, nice. So I've just put in some timings for the biggest system, the 256, which kind of shows the best case scenario in a sense. So in terms of scaling. So for the H2O 256 on one node, the run I ran took about 200 seconds. 2 nodes, it took 127 seconds. That is 1.57 times faster rather than twice as fast. In other words, it's not ideal scaling. It actually amounts to 78% parallel efficiency, which isn't awful, but it means that those 21.5% lack of parallel efficiency is money lost, essentially, is less value for money that you're getting out of your compute budget. Throwing 4 nodes at the problem runs in 112 seconds, which isn't 4 times as fast. It's only 1.78 times as fast. So that's down to a parallel efficiency of 44%. So you're wasting even more money. So in principle, your calculation will go faster and you'll get your answer sooner, but you're wasting a lot more of your own money or your research funders' grant allocation. So that's just something to be aware of, as always with any application, nothing specific to CP2K, but this is how it pans out in CP2K. Okay, in interest of time, let's move on to the second part of exercise 5, which is talking about hybrid parallelism. So we've already mentioned that CP2K can run in parallel in at least 2 ways, ignoring GPUs, namely using MPI parallelism and OpenMP. And we've said that so far in the job scripts that you've been running CPUs per task in the resource request, as well as OMP num threads were set equal to the same thing, namely to 1. So it was running 128 MPI ranks with 1 OpenMP thread per rank. So, but then the idea here is to experiment with what using multiple threads per rank can give you. So if you, in part 2 here of exercise 5, if for the H2O128 case, if you experiment with using 2, 4, 8, or 16 threads, and see what you get. Now, why these numbers? Why not more than 16? Well, even if you didn't already know that, CP2K is extremely unlikely to benefit from using as many as 16 threads per rank, simply because of how OpenMP has been implemented and the nature of the algorithms, etc., etc. Then it's still, you might expect that more than 16 threads might not be a good idea because of something to do with the memory layout of the processors on ARCHER2, which means that cores 16, there's groupings of 16 cores within a processors that access the same memory, that share memory at a low level. At low level meaning fast, low latency, and high bandwidth. So that means that threads that belong to the same rank, if there were more than 16, then one of them at least will be trying to use memory from it, will be trying to share memory from a different grouping of 16, which could be slower. But so have a look, try running a few jobs with these different thread choices, and whatever you choose. So if we look at an example job script, whatever you choose now, you're going to modify the tasks per node and the CPUs per task. Very conveniently, the job script has been set up to automatically derive this environment variable called OMP num threads, set it equal to whatever you specified as CPU as the CPUs per task above, which is convenient. So you only have to change a number once, but whatever you do, you have to make sure that the number of tasks per node times by the CPUs per task is always equal to 128. So you could change, you could do 64 times 2, or 32 times 4, etc., etc. See what you get. Give people a couple of minutes, and then I'll try and summarize quickly, and then we'll be up to the break. Thanks, Maxime. Putting your results in the Etherpad. And if anybody, again, already has any, or once you get some timings for different numbers of threads, please feel free to put them in the chat or the Etherpad. So to use one thread per, it's always it's not there like one thread in absolute terms. It's one thread per rank. So it's a nested parallelism. So each MPI rank, which is like a separate instance of CP2K running in parallel with other instances or other processes, each instance of CP2K has a number of ranks. So each MPI rank has, each instance has a separate different number of threads, as its own threads, I should say. So the question of putting one thread per rank, that is, you set CPUs per task to be 1 and 128 tasks per node. So the answer is yes. And if you want a different choice, you put, for example, CPUs, if you want to run on, if you want to make sure that each MPI rank runs 2 threads, as its own 2 threads, rather than just 1 thread, then you put CPUs per task equal to 2, and you put tasks per node equal to 64. Okay, so see what you get. So when I run it, so I get the following. So with 1 OpenMP thread per rank, it's 54 seconds. Then with 2 is 52 seconds roughly. Of course, you'd have to do a number of these runs and take the average and get statistics out. With 4 threads per rank, it goes up. With 8 threads per rank, it's even worse. And with 16 threads per rank, it's way worse. So this is useful to do because clearly it looks as if, okay, it could be slightly faster. You get a slight performance benefit from using 2 threads per rank rather than 1. This happens a lot with CP2K. Actually, CP2K has often gets a little bit of a performance benefit, maybe from using 2 or maybe 4. Depends on the problem, depends on the architecture, the processor architecture, etc., etc. In some cases, which you don't have time to cover now, it can be very useful to use multiple threads per rank in order to avoid running out of memory. So it's a good example in the CP2K distribution. There's a directory called benchmarks. And amongst these benchmarks, there's one called QS-LIH-HFX, which runs you through a very good exercise about changing the number of OpenMP threads per rank in order to be able to not run out of memory on a compute node. So we've come up to the time scheduled for this session. So we're due a break. I just wanted to very quickly show you one more thing. Okay, so I'll put a link on the Etherpad to the thing I just mentioned. So the LIH HFX example of multi-threading in CP2K to avoid out of memory errors. So that's an example there. And let's see, I just wanted to show one thing. There is something that might be useful for you to be aware of on ARCHER2 if you're an existing user of CP2K running large-scale simulations, or if you're possibly going to do so in future, which is that on ARCHER2, the MPI essentially has there are two alternative implementation layers for the communication underneath MPI. One is called UCX, the other one is called OFI. Here we go. And some experimentation by colleagues has shown that in some cases where if the simulation you run, if the calculations you're running with CP2K or any other application potentially are using a lot of what's called global communications, collective communications, then and if you're running on many nodes, then it could be that switching from the default approach to MPI to the alternative approach to MPI on ARCHER2, namely UCX, the default being OFI and the alternative being UCX, could potentially give a performance benefit. So this is an example showing running. In fact, I think this is the LIH HFX example that I mentioned, running on many nodes. So running on 64 nodes. On 64 nodes, there's not much of a difference between OFI and UCX, but on the 128 nodes, there is quite a substantial difference between OFI and UCX. So in that case, I would point you at the documentation on the ARCHER2 website, where it says switching to alternative UCX and MPI implementation. And there are basically two lines that you put in your job script to enable that. Okay, so I'll leave it at this, leave this session there. So these course materials are not going to be used in any of the other practicals today directly, but they're bonus as a reference to look at, and so the exercises are bonus exercise to just look at maybe in your own time, and some of the explanations are there to look back on as well. What in particular what might be useful is to look at after exercise 1, there is a sorry, not after exercise 1. There's a section here on creating your own input file, which is definitely useful to consider. It talks about things you should take into account when you're setting up your own simulation. So your system coordinates, the cell dimensions, the basis of the potentials, are they appropriate? The SCF setup, the tolerances, what kind of things you need to take into account. Some of these are covered, how to do these in the exercises in these materials. And the choice of XC functional, which is often, a good question mark. So maybe Matt and Anna will touch on the choice of functional, cutoff, relative cutoff, and other things. Okay, so I will leave it there. We'll have a break, and we'll be back again at 1:15 when Matt will talk about basic or a standard DFT.
Right, I guess I'll just go into this. So it's always a bit of a balance running these introductory sessions as to how to decide what material to go. So I will probably, as ever, share a bit too much, a bit too quickly, but perhaps with the idea that at least it will give a little bit of a hint of what's out there to some people. And then you can drop questions in the chat over lunch or in the Etherpad and all these things. There'll be plenty of opportunities to follow up. There'll be a session later with talking about ab initio molecular dynamics and training machine learning force fields and excited sets. So lots of more specific stuff later, but this just want to give a little bit of a flying overview of what CP2K does, mainly in the basic standard ground state DFT calculations, but the same sort of thoughts behind the algorithms are used to inspire the numerical implementations of the other more advanced functionalities. So it's worthwhile to see. So what I'll do is just have a very, very flying overview through some of the ideas behind the numerics, you know, why we've got these grids, why we've got the basis functions, this sort of stuff. And then I will actually try and share a terminal and just running a couple of fairly straightforward water DFT examples and just have a look for the input file. Hopefully you can sort of ask me, what does this mean? What does that mean? And we can sort of have a bit of a chat. So yeah, I've been using CP2K, developing and using it for a long time. It's quite an attractive code for ab initio and molecular dynamics. Being able to look at sort of hydrated systems, for instance, was a big advantage. You could get sort of longer time scales than you could from some other sort of alternatives. If you look on the CP2K website, there's a pretty good selection of interesting papers. You can see it's used quite widely, from sort of traditional quantum chemistry through to much more sort of physics, condensed matter. So it kind of it sort of straddles that border between sort of physical chemistry and sort of chemical physics. And in 2020 there was the latest sort of update paper in Journal of Chemical Physics, which included sort of some fairly detailed discussion, but also a sort of a high level overview of the different functionality that's available in CP2K. So Arno gave a very nice sort of overall introduction. For our purposes, I'm not going to explain where DFT comes from or anything like that, but the Cone-Sham theorems give us an idea, a sort of a numerical recipe for how to calculate the electronic energy and energy levels of a system. And to do that, basically we need to build a Hamiltonian matrix which describes the the energy of different parts of the systems in terms of basis functions. So to have a numerical implementation, we need to introduce these basis functions. And CP2K tends to use Gaussian basis functions as the primary basis functions. So sat on an atom, you've got different types of Gaussians, different widths, and by multiplying them by a polynomial, you can get extra flexibility. So we need to build the Hamiltonian, so that's one thing. And then once we've got the Hamiltonian, we need to diagonalize it, and the eigenvalues and eigenstates are our electronic energy levels. As well as standard DFT, there's a whole bunch of stuff available in CP2K. You can do double hybrids, there's GW, there's sort of MP2 post Hartree-Fock stuff. There's various type binding methods, some of which are truly linear scaling, and you can go up to sort of millions of atoms if you've got a very big computer. Some semi-empirical methods, and there are the sort of QM/MM methods that Arno mentioned before. And there's electronic transport and a whole bunch of other things. So really, what the whole business of setting up a code to do DFT is to construct this Cone-Sham matrix, this Hamiltonian matrix, which sort of tells you about the energy of the system in terms of these basis functions. There are various terms that you need to calculate. It's normally the electrostatics, the exchange correlation, so this strange sort of non-classical interaction of electrons. Possibly, if you're running a hybrid functional, exact exchange, and core and pseudopotential terms, kinetic energy. So we want to be able to evaluate all those energy things, all those energy terms efficiently, and set up a matrix representation, and then we need to be able to diagonalize that matrix. So those are the two things you need to be able to do efficiently. So CP2K has this so-called Gaussian and Plane-Wave method. So it uses everything is centered around the Gaussian. So the first representation of the density is in terms of Gaussian basis functions. So we have a whole load of Gaussians, and products of Gaussians essentially give us a density element. So the density is made up of a sum of the product of our Gaussian functions, a certain amount of this type, a certain amount of that type. Where we've got different Gaussians on different atoms, you end up, the product of them is another Gaussian that's sort of centered between the two atoms, and picks up where they're overlapping. So we always have to cast our density, and then our energy will be a functional of this density. We always have to cast it in terms of these Gaussian functions. And because they're non-orthogonal, we have this so-called overlap matrix. So we actually have a generalized eigenvalue problem. But also because these functions are dropping off as a sort of exponential minus something squared, whilst they always overlap, after some quite small distance, they overlap very in a very sort of limited way. So by cutting off elements of the overlap matrix at a certain value, we get sparse matrix representations, which are used heavily in CP2K. Because we've got this sparse representation, in principle, you can go and set up linear scaling algorithms. There's a bunch of them in CP2K. We're not going to touch on those in this course, but if people are interested, we can get more information about those. So I mentioned these basis sets. There are basis sets that come with CP2K. They're hidden in this data directory that the installed CP2K knows about, and ones will tend to be using these so-called MOLOPT basis sets that have been pretty well tested and are good quality. So they come in two flavors. There's sort of a double zeta, which means for each state of an atom there are two independent basis functions that can represent it, giving it a flexibility, or a triple zeta where you have three of those functions. Yeah, the details I won't go into here. And then at the end, using these basis functions, we have to represent the kinetic energy, pseudopotential or any external fields, the electronic electrostatic energy, and the exchange correlation energy. So the first three terms can normally be represented in terms of analytical integrals over the Gaussian functions. So we can evaluate those very, very quickly and easily with the Gaussian basis function, essentially exactly as Gaussian or ARCHER or another quantum chemistry code would do. But the last two terms, the Hartree potential and the exchange correlation terms, particularly when we're in a periodic system, are a bit more complicated. So what CP2K turns to is an auxiliary basis functions, so it uses plane waves. And what we do is use these plane waves to build up an equivalent density. So it represents, at least on the grid points of the plane wave, essentially the same density as the Gaussian representation of the density would give us. So there's a sort of a mapping. We've got some sort of Gaussian. We see how much of that Gaussian, what its value is at each of the grid points. We add it up for all the Gaussians, and we end up with a plane wave or a grid representation of the density that's, if everything is set up properly, is numerically equivalent to the Gaussian representation. This is called co-locating, putting the Gaussians onto the grid. And so that is the step where we, as well as defining the Gaussian basis sets, we define this multi-grid thing, this set of grids that we're going to map the Gaussians onto to get this equivalent representation using these regular grids. And why do we do that? Well, it turns out that we can actually evaluate the electrostatic terms and the exchange correlation terms very easily on these grids. So we can run exactly like a plane wave code, like Quantum Espresso or something like that, in terms of collecting the electrostatics, we put the density on these grid points, we Fourier transform it, and then you can basically write down the energy of the system. And then what happens after we've got the grid representation of the potential from the Fourier transform is we then integrate it over our Gaussian functions to get back our Hamiltonian in sort of language. It can be worth having a look at the timings. You'll see at the end of the output files that there's a whole bunch of information comes out. You can see that in the example I've got here, there's this sort of build the Coombe-Sham matrix. So you can get an idea how long it's taking to actually construct all the energy terms. And then there'll be another part on top of that where it will actually be calculating the energy levels and eigenstates. So it'll be a diagonalization term. And what tends to happen is for larger systems, the diagonalization part, which scales less well, starts to really take up the time. And that's where you might shift to these linear scaling methods. I won't go into any details here, but you can run all-electron and CP2K by changing to this sort of GAPW method. This can have quite a lot of benefits if you want to, if you want to be able to describe the core electrons, if you want NMR or EPR or other things that depend on, or XAS signals that depend on core electrons. Okay, that's the flying view of the building the Hamiltonian, and then just a couple of quick comments about once we've got the Hamiltonian, how do we diagonalize it? How do we get the eigenvalues and eigenstates? There's more methods available, but broadly speaking, there's two. There's this sort of traditional diagonalization, which is the standard stuff that you pretty much learn in linear algebra class, and this other one that Arno mentioned briefly, this orbital transformation. So the self-consistent cycle that Arno mentioned was we construct a guess at the density. From that density, we construct this Coombe-Sham matrix, so this sort of matrix with the energy in terms of basis functions. Then we diagonalize it to get a new set of eigenvalues and eigenstates. We possibly mix together the old guess at the density and the new guess at the density in some ways, and then we keep going round in a circle, and if things are well, the energy the system will be dropping down, and eventually the density will not change. So it's sort of a fixed point problem. The density we put in is the density we get out, or numerically close enough, and we decide we're at convergence. I will fly through this. If anyone is actually really interested in the OT method, some of the maths behind it, there's some quite detailed notes from Yang Heng there that's linked in. So we're solving this generalized eigenvalue problem. So this C matrix, which contains the eigenvectors, they are our wave functions, our Coombe-Sham functions, which tell us where the electrons would like to be, and the E is matrix, diagonal matrix with the eigenvalues of the molecular orbitals. So we can do the standard diagonalization. It just goes in the SCF section, and there's just a little thing we say mixing. So this one is we'll take 0.2 of the new guess, and we'll keep 0.8 of the old, so the density doesn't go sort of crazy all over the place. And then it checks whether there's a big change in the density matrix, and if it's not, it decides it's converged, and we move on. And what you'll see is something like this, that you see this convergence, which for standard diagonalization is telling you about how much the density matrix has changed, the largest element of the density matrix, and you see that it's getting smaller and smaller, and eventually it should converge. And you've got a change in the energy as well. So as well, whatever your criteria is, you want the total change in your system energy to be below micro hartrees, I would suggest. Otherwise, you're your solution is not close enough to the ground state to get reliable energies. CP2K is not so good with metallic systems, but it does have the various functionalities available there. In that case, instead of putting whole number of electrons into individual orbitals in the sort of alpha-Val principle, filling up from the ground upwards, we actually use a Fermi-Dirac kind of distribution. So we put fractions of electrons, so it's sort of an ensemble of electronic systems, and we put the statistically sensible number of electrons into each system and define the Fermi energy based on that. And there's an example linked in the shared folder, but we essentially tell it to smear out the electrons to apply this sort of fractional occupations with some electronic temperature, and we typically use this Broyden mixing, which is just a way of achieving convergence. It's a sort of quasi-Newton way to get this self-consistent cycle working. But CP2K tends to shine for insulating systems, and then there's this method called orbital transform that is really quite robust and fast. And what it tries to do is to find a way to directly minimize the density matrix that's the ground state of the system, without having to do the diagonalization. The downside of doing a direct minimization is that you somehow need to ensure that the eigenstates of the system remain orthogonal, so you don't just get the wave function just sort of collapsing. And this is achieved through a fancy transformation of coordinates that I'm not going to mention. I say, if you look at the previous PDF from Lian Heng that I linked, it gives you quite a lot of detail. So this direct minimization with OT relies quite strongly on preconditioning the problem. I'm not going to explain what that is. Some of you, if you had courses on numerical analysis, will understand what I mean. But it essentially recasts the problem into a simpler problem where various matrices are closer to sort of diagonal unity. So it's a less numerically challenging problem. So there are various preconditioners that can be applied based on approximating the Hamiltonian as perhaps just a kinetic energy term, or perhaps some other bits and pieces. So making an approximate guess to the solution and transforming the problem based on that. That's where this outer SCF loop that Arno mentioned comes in. So at the beginning of the loop, this preconditioner is applied to the problem, and then the SCF steps go on. But then if it's slowing down and the inner loop doesn't converge, we go to the outer loop, and then with this new density, a new preconditioner is applied. And if we're relatively close to the solution, we should get a very good preconditioner. And then after this outer step and this new preconditioning, often will then converge really quite quickly. So that's why it's a good idea to have this outer SCF step, and perhaps a moderate, maybe 20 or 30 inner SCF cycles, and then going to the outer, reapplying the preconditioner. So this only applies to OT. It doesn't do anything for the traditional diagonalization. So this has been my sort of standard setup. So if you've got a guess, if you've got a previous guess from a system, use it. We want to converge the wave function. The exact details of what this means I won't go into, but around about 10 to the minus 6. But check that the energy of the system is only changing by very small amounts. So about 20 to 30 SCF cycles in the inner loop. There's this settings for the OT. I would say these are fairly sensible for small systems. And then the outer loop, you don't want to do more than 1 or 2. If it's not converging after 1 or 2, it's probably a problem. Probably your system is metallic. For large systems, there's a different preconditioner. It's not quite as good, but it's much cheaper to construct. Why would you use different ones? OT only works for insulating systems, so you've got at least, let's say, 0.2, 0.3 electron volt band gap. If you haven't got that, OT is going to really struggle. If you've got a metallic system, then you need to use diagonalization and you need to use smearing. There are some differences sometimes in the outputs you can get from the code, but I won't go into this now. So that's the basic settings. You know, the tiny bit about the numerics, how we get the Cohen-Sham matrix, a little bit about the diagonalization of OT for diagonalizing or minimizing the density matrix. I'll just couple of tiny things to mention. You can run MD. San Liang and Lo Li are going to go into detail in that after lunch, but you can also do geometry optimization. You can do cell optimization, where you've got the periodic system and you minimize the stress tensor as well as the forces on the atoms. Yeah, there's lots of stuff about molecular dynamics. There's a YouTube link that we did. There's a whole series of videos that we recorded in Ghent a few years back, a horribly large number of years back, in fact, but they're very good. And I've not gone into it. Everything we're going to show is just sort of command line traditional editing with a text editor, but there is integration with the atomic simulation environment, this AIDA sort of throughput and sort of metadata validation infrastructure that's again developed as part of this Marvel program, largely in Switzerland. Oh, I don't want to do that. And I've put a few test systems in work TA154 shared. In fact, I put it in /vanilla DFT. I updated that at the last point. Let's change that. There's a run script there which has the various input files, but essentially it's the same as the one that Arno gave you earlier. All you need to do is change the input name of for the appropriate input file. So what's there is a H2O using, so it's just a 64 water molecules, a bulk system, and run using PVE. So you can play around with that. Again, it's got a, I'll show you in a second, it's got a variable you can do to change the system size, so you can scale up the system and see how it changes. You can play around with how many cores you can push as your system gets bigger. And then there's a follow-up calculation that reads in the restart information, the wave functions from the GGA calculation, that runs a hybrid PBE0 calculation for the same water system. I'll talk a little bit later on, just very briefly, about some of the details of the hybrid functionals, this exact exchange later on, but if you want to just play with it and see how it performs compared to the GGA, it's there. And there's also an example of this traditional diagonalization, just a sort of a copper system. So you can have a look at those. Right, I don't know if there's any questions or anything about what I've said.
I don't see any questions in the chat.
Excellent. I've either been very clear or completely incomprehensible. One of the two, somewhere in between. Let's see. So here are the files. I just got them from, what is it? There's some input files there, various bits and pieces. So I just copied them into this.
One question in the chat.
Let's have a look. Am I going to get infinite wall of mirrors? Yes.
I can read it out for you if you like.
Yeah. Yep, go for it. Go for it.
Okay, so as Jay's asking, quite confused about GPW, is it integrating two basis sets?
So the way to think about it is that everything is done with Gaussians. So it is always the Gaussian basis set the quality of the calculation is only as good as the Gaussian basis set. But to calculate two particular things, the exchange correlation potential and the electrostatics, it's convenient to project the Gaussian density onto an equivalent representation in plane waves. So what we do is we see how big the Gaussian density is at a point in space, and then we assign that point of space on the grid the same value. And we do that on a regular grid. So at least on the regular grid, the Gaussian and the plane wave have the same values. And then there are some tricks to allow us to calculate the electrostatics and the exchange correlation potential very easily, this grid representation. And then we integrate back, we convert it back into the language of the Gaussian thing. So we momentarily drop out of the Gaussian thing to a plane wave way of looking at things to calculate a couple of things, and then go back to the Gaussian. So the plane wave one is only an equivalent to the Gaussian one, so you don't suddenly get plane wave accuracy by having this backward, this sort of auxiliary thing there. But you've always got to have this plane wave, so you've always got to have this this setting and check that it's sufficiently good to get a good representation of your Gaussians. Because if you've got very spiky Gaussians, you need finely placed grid points to represent them.
I'll get on to another question. Yeah, I think Jay says thanks, but then also a follow-up question. I'll get to Maddie in a second, but a follow-up question to that is, okay, so then how does this code describe the periodic system?
So the way it works, is through this, get myself confused, too many slides, through the overlap matrix. So we have, you know, our atoms are inside a box, but then there is a periodic replica of it. And so some Gaussians could be very long range and go across multiple boxes, and then we're sort of adding up the images until we go far enough. So we end up with a description in terms of just the primary cell, but it includes the interactions of the images neighboring each other. And the density is periodic in that sense. And when we do the conversion into the plane wave representation, solve for the electrostatics using Fourier transforms, that's done in a periodic way. You know, the Fourier transform is periodic in the cell. So essentially everything is dealt with periodically, so that the interactions with the images are built into the overlap matrix and the Hamiltonian for the within the primary cell. Again, I don't know if that answers the question.
Jay says crystal clear. So I guess crystal without the periodic implication of crystal, maybe, or pun intended. But the question from I'll go back to a question from Maddie. Actually, two questions. One is, as you mentioned, OT is for insulating materials. If I'm modeling MOFs, which are primarily insulating, but I want to look at their conductivity, if I alter the structure, would I no longer use OT?
It depends how you want to measure conductivity. So if you have essentially still an insulating system, but perhaps you want to look at the density of states and you want to see how maybe the density of unoccupied levels or levels around, you know, the highest occupied state are changing due to how you're changing it, and then making inferences about conduction based on that, then, you know, you could carry on using OT. If you actually want to calculate conduction in some other way, then you know, if you're explicitly doping it heavily and producing something that is closer to a you know, sort of a, it's not a metallic system, but where you've got a very, very small separation of energy levels, then you might have to go to smearing. You normally know quite quickly whether OT is working or not. You can look at the energy levels. You'll see the acceleration slowing down. I mean, the convergence slowing down extremely quickly if you start getting very close to a metallic system. It'll get quite close, and then it just won't be able to find a stable solution. Some MOFs, of course, are quite heavily metallic, so you know.
I was going to say, yeah, Maddie says, okay, amazing, thank you. But I say, Maddie, why don't you unmute if you like and just ask your second question as well and respond to what Matt was saying, if you like.
Yeah, hi. Thank you for the answer on that one as well, as I'm quite new to trying to understand the input files, and I know MOFs are very difficult anyway for CP2K. But yeah, my second question, because I looked at your copper input file, and there's a section VDW potential, and it's commented out originally, and I was wondering what it does and why is it commented out?
Why is it commented out? I was debugging some stuff actually. I'd made a mistake elsewhere, and I was wondering if this was the problem. So, in fact, that could just be uncommented, and you could try it out. So this is using. This is back to the sort of how do you choose your DFT functional, and so for MOFs, indeed, because they've got this space, you do want to have some sort of van der Waals interaction that will be not very well described by some non-local, some semi-local functional. So there's basically two types of van der Waals functional. There's things that look basically like a van der Waals interaction, just some sort of 10 to the minus 6 sort of interactions. These sort of Grimmer type ones that you can include. And the other one is these sort of more ab initio ones from sort of logarithm, whatever, that are these non-local van der Waals ones. So again, both methods are trying to introduce the van der Waals interactions, so this non-local sort of long-range attractive interactions into the exchange correlation function. So that's, you know, sort of a whole separate topic how you choose those, but the various different flavors of van der Waals interactions are pretty well represented within CP2K. So it should work if you uncomment those lines.
Okay, thank you.
Yeah. So I'll just very quickly run those. Let's have a look at. So if you want to play, I've got this. You can set variables inside an input file. So I'm setting this number of repetitions in the x direction to 1 here. And if I go down here, it's the unit. So this periodic cell. It's about 12.5 angstroms in each direction, but it's got a multiple unit cell, and it's replicating it, making the cell however many larger in the x direction. So you can explore scaling. You can make things bigger by just changing that one number at the top, and then see how the cost of the calculation goes, and how changing the number of cores increases things. So that was one. And this hybrid one follows up. Let's make it consistent. Make it more consistent. I'll put it to 3, but I'll just do it. Let me see. Different username. Okay. So this just runs a short molecular dynamics simulation for the GGA calculation. It's just PBE water. Seems to be running very slowly. I guess it's just updating very slowly. So you see the SCF cycles converging sort of quite quickly within 5-6 iterations after a little while. And the main information we get out of this. And what's important for this GGA calculation is we get this wave function file. So it writes out a list of this C matrix that was in the slides, this list of which Gaussians build up the occupied orbitals. And then for the hybrid calculation, it allows us to take the SCF guess to be restart, which I think Arno also mentioned to you in the first section. And so for hybrid functionals, it's very, very important that you read in a good converged GGA guess to go there. Okay, now it's starting to run the hybrid calculation. It's already run the hybrid. So there's lots of information that often you don't need, but it doesn't really hurt to have it around quite often. I'm going to talk a little bit more about the hybrid functionals later on, but it's perhaps interesting just to have a play. And what you see at the top is that there's a whole bunch of stuff where you've got to calculate bits that are required for the exact exchange, and that makes the cost of the first SCF step considerably more expensive. But once that first step has been done, if you have all of your integrals that you need stored in memory, then subsequent SCF steps are hardly any more expensive than a standard GGA calculation. So if you can get stuff into memory, you can really run fairly efficient ab initio MD, even with hybrid functionals. I guess I'm probably sort of.
So Matt, I guess with those examples, the example you just mentioned with the memory there, it maybe connects to what I was suggesting is sometimes useful with CP2K, where you have this max memory keyword, which restricts how much memory you allow CP2K to use, how much memory you allow each rank of CP2K to use. I know you know, I'm just for people. I mean, so setting that value, that keyword max memory, setting that to what you must work out depending on your choice of how many ranks you're running per node and how much memory you have per node, to be the most it can be, so that you get optimal space, as much space as possible. There is a memory for CP2K to use to store those electron repulsion integrals. I guess.
Yeah, so practically you can store about 1.5 gigabytes per thread. So if you're running with 4 threads, you can set that value to be whatever, about 6 gigs or something like that. So that gives you quite a lot of flexibility. And actually the Hartree-Fock, the exact exchange stuff, is the one place where the threading parallelization is almost perfect. So you can benefit quite heavily from that. The rest of the calculation, still loses a bit, but the actual calculation of the integrals is almost perfect with lots of threads. So yeah, it can be a very, very, very good way of getting performance. Yep. So yeah, well, thank you for listening. It's a bit of a hard thing to know quite how much information and stuff to get across in these short sessions. But I think the session with this afternoon with the ab initio MD and the ML will be sort of a bit more hands-on. So you'll start. Hopefully, you've got enough sort of vocabulary now to sort of see what some of the stuff coming in and out is, and to be able to sort of enjoy those sessions.
Great, that's very useful.